Hello everyone, welcome to this 30th lecture in the NPTEL course on Riemannian geometry. So in the previous two lectures we have talked about the local Gauss-Bonnet, and in lecture 28 I also showed how to prove a global version of Gauss-Bonnet from the local version. In today's lecture we will finally complete the proof of the local Gauss-Bonnet. So let me remind you of what we did in the previous lecture. So the setup was as follows. So we are working on a polygonal region which I denote by omega. We are assuming that these are sort of small polygons so that they are completely contained inside a coordinate neighborhood U on M. The boundary is parametrized by this curve gamma, and this is a positively oriented curve in the sense of Stokes's theorem. So let me remind you that basically means that the outward normal and gamma dot of t form an oriented basis for the tangent space of M at gamma of t. So it is a positively oriented curve parametrizing the boundary of omega, and it is a curved polygon with external angles epsilon k, where k ranges from 1 to m minus 1. So our usual convention is that we have a partition a naught up to am of this interval a to b, so that gamma restricted to ak minus 1 to ak is smooth, and we also parameterize so that it has unit speed. And we assume that the endpoints, in which case in this case we are working with a simple closed curve, and we assume that the initial and final point are that is not a vertex of the polygon, which means in terms of derivatives that the velocity vectors at the 2 points agree. So the gamma dot of A is equal to gamma dot of B. Okay. Then in the previous lecture the main point was to construct this sort of tangent angle which we call theta. So this is a function from a to b to r which satisfies the following two important conditions. So if you take an orthonormal frame on U such that E1 is a multiple of del by del x, okay, and E2 is then obtained by the Gram-Schmidt process, then gamma dot, which is a unit vector, is given precisely by cosine of theta t times E1 of gamma t plus sine of theta t times E2 of gamma t, okay, at all the smooth points. And then we define theta of ak to be simply the limit as t approaches ak of theta of t, plus you have to correct for the external angle at that vertex, okay. So k ranges from 1 to m minus 1, so these are all the vertices of the boundary polygon, okay. Alright, and at the end of the previous lecture we established the following corollary, that 2 pi is equal to the summation of all the external angles plus the integral essentially of the derivative of theta. So the integral summation k from 1 to m of the integral from ak minus 1 to ak of theta dot of t dt, okay. So let me remind you what the local Gauss-Bonnet was. So the local Gauss-Bonnet, we are required to prove the following formula, that 2 pi is the summation of the external angles plus integral of this normal curvature of gamma on the boundary plus the integral of the Gauss curvature on the polygonal region, right. So in order to complete the proof from the corollary, I basically just need to relate theta dot to these two terms, right. So that will be the main goal of today's lecture, and that will complete the proof of the local Gauss-Bonnet. So the key point is to introduce this connection 1 form. Okay, so let me explain what this connection 1 form is. So we define this omega is a local 1 form on this coordinate neighborhood by the following formula. Omega of x is simply the inner product of E1 with the covariant derivative of E2 with respect to x. Now because this is sort of C infinity linear in that component, covariant derivatives are C infinity linear in those components, one can check that omega is C infinity m linear and hence a 1 form. Okay, so that's a simple calculation. I'll leave that as an exercise. Okay, but the point is I can now calculate all the covariant derivatives I require using this 1 form omega. So note that because E1 and E2 is an orthonormal frame, this is 0 on all of u, which means that if you take the derivative with respect to some x, that is going to be 0, but by the product rule this is simply the covariant derivative of E1 with respect to x comma E2 plus the covariant inner product of E1 with the covariant derivative of E2 with respect to x. But by definition this is basically just omega of x, right. So this implies that this is given by minus omega of x. Okay, but then by the same sort of reasoning one can check that if you take the covariant derivative of E1 with respect to x and take the inner product with E1 itself, that is going to be 0. How do you check this? You basically apply x to norm E1 squared, that is 0 again, and by the fact that this is a metric connection, this is twice of this, right. So that proves this. Similarly you can take this is also 0, okay, which basically implies that if you take the covariant derivative of E1, there is no component along E1 because of this, the component along E2 is given by minus omega x. Similarly we have this formula. Okay, so these are the key formulae that I am going to use. Okay. Alright, so now let me state an important lemma. I will complete the proof of the local Gauss-Bonnet assuming this lemma, and then I will come back and prove this lemma. So the following is the key lemma, these are the key formulae. So if you look at the normal curvature along the curve, then this is given precisely by theta dot. So the derivative of theta with respect to t minus omega applied to the velocity vector of gamma, where t is one of the smooth points of gamma. Okay, and secondly if you look at d omega, that will be a 2 form that is given precisely by the Gauss curvature times the area element. Okay. Alright, so now let me prove local Gauss-Bonnet assuming this. Okay, so by our corollary from last time, this is precisely the sum of all the external angles plus k going from 1 to m ak minus 1 to ak of theta dot. Okay, but this is precisely k going from 1 to m minus 1, the sum of the external angles, plus by the first part what is theta dot, that is basically kn plus omega, right. So this is I am not going to keep writing this, I am just going to denote the entire sum as basically an integral on the boundary of omega. So on the boundary of omega you basically integrate this. So this is of course understood that you only integrate on the smooth parts, right, plus the integral of omega of gamma dot dt, right. Okay, so note that this integral is precisely equal to the integral on this boundary, which is a one dimensional manifold of the one form omega. This is the definition of integration of one forms on curves, right. So you can rewrite this as k going from 1 to m minus 1 epsilon k plus the integral of the normal curvature plus the integral of this one form on the boundary, but then by Stokes, and here is where the orientation was important, the fact that I have oriented gamma so that it has positive orientation with respect to Stokes's theorem. So now I can apply Stokes's theorem and convert this into an area integral. Of d omega. So this is Stokes. So this is Stokes's theorem. Okay. But then by the second part of the lemma, this is precisely the total Gauss curvature inside omega, okay, because d omega is equal to k times dA. So that completes the proof of the local Gauss-Bonnet. So essentially we have reduced the proof to this these two important calculations. Okay, so let's prove the lemma. So let me rewrite the lemma for your convenience. So or let me do the following. So let's prove the lemma. Okay, and let's write down what the goal is. The goal is to show that Kn of t is theta dot minus omega of gamma dot. Okay, so let's prove let's prove this. Okay, so recall from the previous lectures we had this normal vector field along gamma such that n of t and gamma dot of t form an oriented basis, right. Okay. Also from our definition, what is gamma dot? This is how we had constructed t. So for all the smooth points, gamma dot is precisely given by this. Okay. On the other hand, what is n of t? By our construction, I mean n of t is just perpendicular to gamma dot. So this is given precisely by minus sin theta t E1 of gamma t plus cos theta t E2 of gamma t. Okay. So one can check that sorry, this should be so gamma dot of t and n of t form an oriented basis. One can check that this is the case. So one can check. How do you check that something is an oriented basis? You apply the area element on this and check that that's positive or not. This is a simple calculation, one can quickly check this. Okay, so now let me differentiate this. Let us calculate the intrinsic acceleration of gamma dot. So what is this? I mean, I use the product rule. So I will first differentiate the cosine. So this will be minus sine theta times theta dot times E1. I will just denote E1 of gamma of t by E1 of t, or let me just simplify notation and just call that E1. Everything is evaluated at time t, plus cos theta times the covariant derivative of E1, right, with respect to the velocity vector. Similarly, I then differentiate the sine term plus sine theta times the covariant derivative of E2. Okay. But recall that the covariant derivative of E1 is precisely minus omega of gamma dot times E2, whereas the covariant derivative of E2 is omega of gamma dot times E1. So if you plug that in, the intrinsic acceleration is going to be minus sine theta theta dot E1 minus omega of gamma dot cos theta E2 plus cos theta theta dot E2 plus omega of gamma dot sin theta E1. Okay, so let me, I want to, I mean, what do I want to do? I want to compare. So recall that this intrinsic acceleration is precisely kn times the normal vector n of t, right. So I want to compare this expression to the expression of n of t. So I pull out minus sin theta E1. So if you pull out minus sin theta E1, you collect these two terms and you would have so this is the same, sorry, so this is the same as minus sin theta theta dot minus omega of gamma dot, this entire thing times E1 plus cos theta of the same term E2, which is precisely theta dot minus omega of gamma dot times n of t, which is supposed to be kn of t times n of t, which implies that kn of t is theta dot minus omega of gamma dot. Okay, so that completes the proof of the first part of the lemma. For the second part, it is again a calculation. So I want to compute what this is. So clearly this acting on E1 E2, this form acting on E1 E2 is basically going to be the sectional, I mean this is going to be the Gauss curvature. Why? Because since E1 and E2 are orthonormal frames, this is an orthonormal frame, one can check that this is always 1. Okay. So this is the Gauss curvature, but the Gauss curvature is precisely given by this, right? It's the sectional curvature of the tangent space, and the sectional curvature is given by this, but because it's an orthonormal frame, this is the same as this. Okay, so I have to calculate this Riemann curvature tensor term. So by definition, this is going to be nabla E1 nabla E2 on E2 comma E1 minus nabla E2 nabla E1 E2 comma E1 minus a term coming from the Lie bracket. Okay. So note that for any vector field x, nabla x E2 inner product with E1 is by definition omega of that vector field, right. So the final term is by definition this. So let us simplify. So this is equal to nabla E1, you have nabla E2 of E2. So right, so maybe let me write some extra steps. So we have this minus the final step is given by this, the final term is given by this. Okay. So now here I again replace this by just omega of E2 E1 and replace this by minus omega of sorry, you are differentiating E2, so this is also plus, so this is going to be omega of E1 E2. Okay. So let me make those replacements. So you have this applied to omega of E2 E1 inner product with E1 minus this applied to omega E1 of E2 E1 and then of course the final term. Okay, now you apply Leibniz rule. So Leibniz rule, you will have first E1 applied to omega applied to E2 times the inner product of E1 with E1, which is 1, plus you will have omega E2 this minus E2 applied to omega of E1 again times the inner product of sorry, this should be I made a mistake here, this should be E1. So whenever you differentiate find the covariant derivative of E2, you get something in the direction of E1, right. So this should be the second term should be E1, right. Right. So this should be E1. Okay, so now you get this times the inner product of E1 with E1, which is 1, and you get another correction term, namely this E2 E1 E1 and then of course the final term, which is this. Okay. All right. Now whenever you differentiate E1, this is going to be omega E1 with a negative sign times E2, but then the inner product of E2 and E1 is going to be 0. So, this term is going to cancel out, similarly this term is going to cancel out, and you are going to be left with E1 of omega of E2 minus E2 of omega of E1 minus omega applied to the Lie bracket, right. But then by definition, by the intrinsic definition of the exterior derivative, this is precisely this. Okay, so that proves the second part, and hence this completes the proof of the local Gauss-Bonnet. Alright, so maybe that is it. After a lot of hard work, as reward we have this beautiful sum angle property now generalized to arbitrary polygons on arbitrary curved surfaces, right. Okay, so this brings us to the halfway point of the course. From next lecture we will start the second part, namely metric geometry. So, we will talk about things like geodesics, distance function and so on, and towards the end of the course we will relate the study of geodesics, the local and global study of geodesics, back to curvature. So, that will sort of tie up both the parts of the course, and that would be a good point to stop the course. Alright, so that is it for this lecture. Thank you for your attention, and I will see you next time around when we start our discussion of metric geometry. Thanks.